For our second problem involving springs, we're going to look at a 5 kilogram mass is placed on a spring with a spring constant of 25 newtons per meter. The force is applied to the mass, causing it to stretch. So this would be like an impulse. At t equals 0, remember that we can start our time at any point. Doesn't have to be at when the spring is at its maximum. It can be at any time. So at the t equals 0, the spring is 5 centimeters from the resting position, or the equilibrium position, with a velocity of 15 centimeters per second. We want to find the equation for the distance of mass in terms of t. So let's look at our general formula. X function of t is equal to a cosine omega t plus phi. And we know the distance at a particular point in time at t equals 0, and we know the velocity at t equals 0. So we're going to have to use the velocity function here. So velocity function of t is equal to negative a omega cosine, oh sorry, not cosine, sine, of omega t plus phi. And what we're really looking for with these two equations and the information in the problem is the values of a and phi. So how would we do this? Well, first let's put in 0 for t, and that's going to give us x at 0 is going to give me a cosine. T is 0, so it's just going to be cosine of phi. And x at 0 is 5 centimeters. Put in velocity at t equals 0 is equal to minus a omega sine. T equals 0, the omega t goes away, and I have sine of phi, and that's going to equal the 15 centimeters per second. Now, how do we solve for a and how do we solve for phi? Let's take and solve for the sine function. We want a sine, so that's going to be equal to negative of the velocity at 0 divided by omega is equal to a sine phi. And now, if you notice, I have a sine of phi, and I have a cosine of phi, and I need to get rid of these trigonometric functions. It would be nice if I could get them into one trigonometric function, and the way that I'm going to do that is I'm going to take and divide this initial condition for x into my function for the velocity. It's going to look something like this. Minus velocity at t equals 0 over omega times x at t equals 0 at that point, and that's equal to a sine phi over a cosine of phi. And that's nothing else than the tangent function. The a's are going to drop out, so I have the tangent of phi is equal to the negative velocity at 0 over omega times x at 0. And so phi is just going to be the arctangent of negative v velocity at 0 over omega times x at 0. And how do I get my amplitude? Well, once I get the angle, I can put this back into either this equation or this equation, and I can come up with my A value. So I'm given the mass is equal to 5 kilograms. The K of the spring is equal to 25 newtons per meter. My X initial is 5 centimeters. And my V initial is 15 centimeters per second. Omega is equal to the square root of K of the spring over the mass, and that's equal to 25 Newton per meter over 5 kilogram. And the square root of that, and that's equal to 2.236 per second. Phi is equal to the arctangent of negative VO, V initial, divided by omega times X initial, and that's equal to negative 15 centimeters per second. So the arctangent of negative 15 centimeters per second divided by 2.236 per second times, and we have 5 centimeters. And this is equal to, if we put it into degrees, it's 50 minus 53.301 degrees. Normally we keep phi in degrees. And now my amplitude is just going to be my initial x divided by the cosine of phi, and our amplitude comes out to be equal to 8.367 centimeters. So now we can write the equation. x function of t is equal to our amplitude, 8.367 centimeters, times the cosine of omega, which is 2.236 per second, times t, minus 53.301 degrees.